Hi everyone. Last year we introduced Spark and DAOS integration. So today I'm going to share you some progress being made since then. I focus on the DAOS asynchronous API support and performs tuning in Spark. Here the agenda. First of all, I'll go through some Spark and DAOS overview, and then I'll go through some work in the DAOS asynchronous API support in Spark. In last item, I'll show you some performance tuning case in Spark. First of all, it's Spark DAOS overview. So in Spark, typically we have two types of clusters. On the left, it's co-located cluster. Spark usually gets input data from HDFS, and in the map task, it will process the input and shuffle data to local file system, which is for the later reduce task. Reduce task reading some shuffle data from local file system. After it's done, it will save the output data back to HDFS. And on the right, it's disaggregated cluster. If you can see the compute cluster and storage cluster are separated. And if we use DAOS as storage, we Spark get both input and output data and shuffle data are in DAOS. For input output data, we use Hadoop DAOS to read and write data to DAOS. And for shuffle data, we use DAOS object API directly. What is Hadoop DAOS? It's just a DAOS implementation of Hadoop file system interface. Just like HDFS is an implementation for local disk. And the S3A file system is the implementation of AWS. So you can see we have some DAOS Java wrapper and the DAOS DFS library. You use DAOS DFS library and we can access DAOS storage. Besides the Hadoop DAOS, we have a Spark Shuffle plugin. You can see in the shuffle process, each map task partition and shuffle data to different D keys, which are for specific reduce tasks, for different reduce tasks. And for both shuffle write and shuffle read, we use DAOS object API directly. Let's go through some work in the DAOS asynchronous API support. So DAOS asynchronous API is event-driven, and each task or operation is bound to an event, which belong to an event queue, from which we can pull the complete list of tasks later. Yeah, it's one of its characteristics. And another one is there's only one default event queue per process. It may be good for some native application, but for JVM, it could be a bottleneck for some ANIC like Intel OPA if there are a large number of threads within one JVM process. I'll show you some performance data later about Intel OPA. And for the there's Async API design in Java. First of all, we need some Java wrapper classes to wrapper native DAOS event queue and its events. This Java wrapper classes are foundations for both Hadoop DAOS and the remote shuffle plugin. So instead of use one global default event queue per process, we use one event queue per thread. There are multiple many advantages. For example, avoid potential bottleneck and also avoid memory sync among threads for different event-related objects. And the number of events per event queue is configurable. And we did some tests on the Intel OPA network with PSM2 provider. You can see there's some performance data, and we use workload DFS IOE. It's just a workload to read and write data directly to DAOS. There's 30 threads within one given process. We got for sync read, the performance is very poor. It could be a bug in Intel OPM, but but for asynchronous read, they are more than 1 GB per second. So to support asynchronous API in Hadoop DAOS, we need to refine code to abstract IO layer so that both synchronous and asynchronous implementation share some common logic. For the asynchronous application, first of all, we need a DFS IO description object to describe the IO to DAOS. Then we need to get an event from DAOS event queue, which is bound to the DFS IO description object. After that, we can call DAOS abstract method, asynchronous method. Later, we can pull its completeness from DAOS using the DAOS event queue. Here's some performance data with the DFS IOE on the verbs NIC WOF cluster. For the read, both synchronous and asynchronous performs equally, almost reach the roof line. It's the results from several months ago. I think the performance should reach the roof line in recent improved code. So we'll update to you if I got the latest result. And for the right, asynchronous API is performs slightly better than synchronous API, especially when there are more cores per executor. So here is, for example, we have total 80 cores, but we split it to different executors, and each executor has 2 cores. So total we have 80 cores. So does the subsequent columns. And besides the Hadoop DAOS, we did support the asynchronous API in Shuffle plugin. Same as Hadoop DAOS, we need to abstract IO layer. And there are 2 interfaces, DAOS read and DAOS write. We also have the asynchronous implementation here for both interfaces. Same as Hadoop DAOS, we use asynchronous simple data description, IO description, and we got event from event queue, DAOS event queue, and bound them together before calling the asynchronous API. Then we pull its completeness from DAOS. Here the performance data with workload scalar in memory repartition. And the shuffle block size is about 200 kilobytes. And here, both synchronous and asynchronous API reach roofline. The roofline is got from the DAOS IOR. For the write, asynchronous API performance improved performance about more than 10%, especially when we have more cores per execute. Like when we have 20 cores, we get a better performance in asynchronous API. Here we use 100 cores, so also split by executor. Okay, then I'll show you some performance tuning, just one case in Spark. We benchmark a lot of workloads, and we find a performance issue in map signed combined workload. So first of all, what is map side combine? For example, on the left, there are 8 records. Each record is in key value pair. When map task processes records, all records with same key, like this one, this in shuffled column in middle, all records with key value of 1 should be combined before shuffle write to DAOS or HDFS. So this column, the shuffled column, is expected result, all records being combined when they have same key. But however, we got some this for the map side combined workload, we didn't handle it very well. So you can call it it's a partially combined. It's partially combined because there is no spill. For example, if when we combined the 2 records, John and Tom, and there is no much memory left in memory, we need to shuffle it right to DAOS. But actually, we should, sorry. But actually, we should spill the temporary R1 records to DAOS or either DAOS or local file system after all records being consumed. We then read them back and merge with R5 so that we can reduce the total number of records being shuffled out. With this partially combined records, will induce memory and computation pressure in reduced task. It will get very bad performance in reduced task. So here's the process for vanilla Spark. It spills temporary shuffle records to local disk. You can see if there is memory pressure here, we sort and spill to local disk. So you can see for each single task, we may spill multiple times. And after all records being processed, we do a final merge sort and combine all these temporary shuffle records and save it to a output file. For DAOS, we replace local disk with DAOS. So all other processes are kept, just the destination is different. So here is some example. For example, we have more than 1 million records as input. And when there is low spill, we still got more than 1 mini records when shuffle right, shuffle out. When we apply spill, you can see it's almost the same number of records in input, but we only get about 20,000 records being shuffled out. So when there is no spill, the reduced task has been running for 20 minutes, but none of the reduced tasks completed. And after we apply spill, you can see all reduced tasks completed with in 4.3 minutes. So it's huge improvement. In future, we'll test and benchmark more workloads. Yeah, that's all.